All right, hi everyone, we are back and we are going to do our Pset 5 solution video. So let's look at the stress strain curve below. Which material is stiffest? So highest Young's modulus, that's going to be the black curve. I'm just going to say black instead of BL. What is the toughest? Assuming that they all have the same volume, that's the total area under the curve. So that's going to be my blue curve, strongest in terms of ultimate tensile strength. So the highest strength, so that's going to be the black curve as well. Yield strength, black curve. Most ductile, blue curve. Most brittle, that's also going to be the black curve. For the blue curve, indicate what is the quantitative value of this failure strain, all these values here. So if I'm looking at blue curve, what am I doing? Blue curve. So if I'm looking at the blue curve, I'm looking at my yield stress is right here. It's probably about 250 megapascals, a little bit less, 240. My ultimate tensile stress and stress at failure looks to be about 1250. My strain at failure is 1. My yield strain would be something like 0.01 or something like that. Great. That's number 1. So nice. So let's go here. The following metallic material, so we know the Young's modulus of a metal, under the stress strain seen here, we're given these dimensions. The red material is sandwiched between 2 rigid blocks, but it's not attached to the blocks. The final length in the one direction is 18. Thermal expansion coefficient is this. Write out the full stress and strain tensor. So first step, coordinate system, we've got it. Second step, material, Young's modulus equals 100 gigapascals. Our Poisson ratio is 0.3 because it's a metal. And now we can start to write out what's the stress and strain tensors here. So in this material, we're just pulling, there's going to be stress in the 2-2 direction that we're being pulled. It's sandwiched between the 2 rigid blocks, but we're going to assume frictionless. There's not going to be stress in the 1-1 or the 3-3 because the material is actually getting thinner. So we're going to expect an epsilon 1-1, an epsilon 2-2, and an epsilon 3-3. We should expect this to be negative, this to be negative, decreasing, this should be positive, and this should be positive as well. And we also know what is that strain in the 1-1 because we're given that final dimension, so we can actually go ahead and start to solve this problem. So let's go ahead and actually pull. I'm going to minimize this, and we're going to bring it over here. Actually, I'm going to solve it right here. So we're going to say that our Young's modulus is 100 times 10 to the 9th. We're going to say our nu is equal to 0.3. We're going to say, what else? Our alpha is equal to, thermal expansion coefficient here is equal to 2.7 times 10 to the minus 8. Our del T, we're not given any mention of the change in temperature in this problem, so we have to assume 0. So our thermal expansion strain, or thermal strain, is going to be alpha times del T. What else do we got here? Let's go ahead. Let's set up. We know that sig 1-1 is equal to 0. We know that sig 3-3 is equal to 0. We know that E11 is equal to, we're told that the final length is 18 millimeters. So strain is final length, 18 times 10 minus 3, minus initial length, which I believe is 20. Yep, 20 times 10 minus 3, and then divided by 20 times 10, 20 times 10 minus 3. Great. Final length minus initial length over initial length, that's going to be our strain. And then we're going to say E1 equals, and then E11 set equal to 1 divided by Y. And then we're going to go basically through our Biddle equation. So we're going to say sig 1-1 minus nu times sig 2-2 plus sig 3-3 plus ET. We're going to copy and paste this. We're going to do it. E2, second equation, is going to be E22 sig 22 sig 1-1. And then finally E3 equation, 3, and then we're going to say this is sig 1-1 right here. Great. Now, I always like to kind of actually open this up because it tells us and shows us what are unknowns. So sig 22, E22, E33, and we know that E11 is negative. It's fantastic, so I can say solve E1, E2, E3. Those are our values, positive, just like we estimated for E22, negative for E33, and sig33 is positive. And there we go. We got it. Full stress strain tensor. Write out the principal stress values. So are we in a principal stress state? Yes, we are indeed. So we are in a principal stress state. What about maximum shear stress? So maximum shear stress, we can do this multiple ways. And actually, I'm going to show it right now. Let me see if I can. I'm going to open up. Let's see if I can change this here. I'm going to go to my Moore's transformation. I'm going to get my handy linear algebra, and we're going to solve this problem in two ways. So if we know that, basically we know that if we're in a principal stress state, the rotation to maximum shear will just be 45 degrees. We also know that it's basically that maximum shear value is just going to be sig1, which is that, minus sig2, which is 0, divided by 2. So that's going to be our maximum shear stress value. But we can also solve that as well. And actually, I'm going to just copy and paste. I'm going to make this a little bit easy on myself. So actually, we'll save this, put this here. I'm going to copy and paste all this good stuff. So we can prove that we're also in a principal stress state as well, just for fun. So I'm going to say stress OG is equal to, and I'm going to say because we're in a principal stress state, we're in a plane stress state, either 2-3 or 1-2, doesn't matter. So I'm going to say this is going to be my normal stress. My other normal stress is 0, and my other normal, or the shear stress is 0 as well. So if I do stress OG here, if I solve for, this is solving for, again, when that third equation is going to be equal to 0. So what's the rotation to principal stress? 0. Great. What about the rotation to maximum shear, which is this, the derivative, stress OG. And we see that it's 45. And if we actually do that, take, for example, T dot stress OG slash dot theta goes to 45. And we indeed see, look at this value right here. That's our center. And then actually our shear stress value would be this. Positive or negative, doesn't matter, just depends on rotation. Fantastic. All right. So we've done this and we've done this. Okay. So now the force is pushing inward like this. And we have room temperature to 310. So we're increasing in temperature. And the force applied is this value here. So let's look at our new stress tensor. So if we're pushing in, so there's a stress 2-2, which is going to be negative. If we're pushing in, there's going to be a stress in the 1-1 and a stress in the 3-3, because the material is wanting to expand. And therefore, there's no stress, there's no strain here, there's no strain here. There will be a strain in the 2-2. So that is kind of the key idea here. Now, wait a second here. I think I made a little mistake. So there will be a stress in 3-3. There actually won't be a stress in the 1-1 because we're still able to kind of basically pop out there. But the 3-3 is limited. So there also will be a strain in the 1-1. I would imagine, and it has to be, strain in the 1-1 must be positive. Strain in the 2-2 will most likely be negative. That's definitely going to be negative. The stress in the 3-3 will also be negative as well. So let's go ahead and let's modify our little expressions that we had here. I'm going to quick kernel abort because I want to clear all those variables. And now I want to do my kind of new expressions. So I'm going to say, for example, E33 is equal to 0. The delta T is now 310 minus room temperature, which is 298 Kelvin. We know that sig11 is 0. And we don't know anything else, but we do know that sig 2 is equal to, we're told the force, which is implied, so it's applied there. So the force is minus 12.7 times 10 to the 3. And we're going to go ahead and close this and divide by the cross-sectional area, which is going to be the length of 1 times the length of 3, the original length. So the length of 1 is 20 times 10 to the minus 3 times, I'm always horrible about this, but I just like to put extra parentheses. Length of 3 original is 3 millimeters. 3 times 10 to the minus 3. Is that correct? Two direction is 40. 3, yeah, exactly. 10 to the minus 3. Now we got that. And I think that's pretty much it. Let's double check. This is why I love Mathematica, because we could actually like visualize and see what's happening here. In terms of like, did we define everything correctly? Are we solving for our unknowns? So for example, like we know what this is. So our only unknowns are this, this, and this. Let me pull up let's see what we got. So we don't know what epsilon 2 is. That is indeed correct. I think I still had, oops. Don't die. Yeah, we don't need that dynamic evaluation. Unfortunately, I still have the description of E11. So again, that's why it's good to double check. I'm going to quit the kernel one more time. Actually, we quit on its own. So let's see what we got. Because we should be solving for E11, we should be solving for E22, we should be solving for sig33. And you can see it's all about kind of making those assumptions, and then we see we do have that. So now we can solve those three equations for the three unknowns. It's taking a little bit. Hopefully your computer is going a lot faster. The new updates, it's really dragging. But while we wait for that, we can actually solve or actually set up the rest of the problem. So write out the principal stress values. We are in a principal stress state. We're in a plane stress state. We're in 2-3 plane stress. So we're in a principal stress state already. Maximum shear is going to be that 45 degrees. So that's going to be the rotation. And we already have the principal stress. If I want the maximum shear stress values in this one, whichever one of these is larger, so let's say I say this is sigma 1, this is sigma 2. Remember, if I'm in a principal stress state to get to maximum shear, that value will just be sigma 1 minus sigma 2 divided by 2 for the maximum shear stress value or your radius. Let's see. I'm going to report evaluation. I don't know what's happening here. Evaluation. Report evaluation. Report command being evaluated. Report. There. Let's try again. There, that's a lot nicer. So we said E11 is going to be positive, excellent. We said E22 is going to be negative, excellent. And we said that sig33 must be negative, and we got it. Fantastic. All right. Turns out in the previous scenario, there was another shear stress, and that was going to be a sigma 1,3 minus 15 megapascals. Write out the principal stress, shear stress values, et cetera, et cetera, et cetera. So if we have a stress in the 1,3, so for example, we have stress 1,3 now, stress 1,3. We'll also have a strain 1,3 and a strain 1,3 here. This means, since we have all three indices, we're no longer in a plane stress state, and we cannot actually solve that problem. But we can indeed actually calculate what that strain is. So E13, remember, will be equal to, if we have that shear stress, it's going to be equal to 1 divided by y, and it's just going to be 1 plus mu times sig 1,3, which is just going to be minus 15, 10 to the 6. And there we go. We got it. So that's pretty much, plus mu times this, that's pretty much that part of the problem there. Now it's saying, okay, well, now suddenly we have this epsilon 2, 3 that's a certain value here. Okay, so now this changes the game. So if we add this value here, and actually we're going to solve for it. We're going to solve and we're going to say, so the other one doesn't exist. So we're going to say minus 0.012317. Set this equal to 1 divided by y times my 1 plus nu times sig 2, 3. Sig 2, 3. So sig 2, 3 is now equal to this. So now sig 2, 3 equals this. Sig 2, 2 equals this. And then we found that sig 3, 3 is equal to this. So now I can actually set up my stress OG. So now we're in a plane stress state, but we are not in a principal stress state. So my stress OG is going to be sig 2, 2, sig 3, 3, normal, normal, and then shear. So what's the rotation to get to principal stress state? Any of these values here. I'm going to, oops. That's not good. I'm going to pull out this value here. I'm going to say, first of all, please stop giving me t dot sig stress OG, actually. I usually do sig OG, but anyways, theta goes to this value here. We should expect to see a 0 value on this last, which is pretty close to it. We could do a couple of ways to get to the maximum shear stress state, but we might as well use our nice function here. 50, again, you keep continuing to rotate. Once you're in that principal stress state, another 45 degrees, and we can do t dot stress OG slash dot theta goes to here. And that's where my shear stress is maximized. And you can see this will just be equal to effectively this minus this divided by 2. There it is. Fantastic. All right, let's go to our last problem, our nice old friend, thin-walled pressure vessels, our favorite. So let's go ahead. I'm working with a new polymeric pipe now, material with a length of this, thickness this, 2 strain gauges, etc., etc. So we always know if I'm working with a polymer, that's going to be 1 gigapascal, our approximation. Nu is equal to 0.4. Del T, there's no mention of that on this problem, but we're just going to set it equal to 0 just to be nice and consistent. And we're going to go ahead, because we're going to use our other values. So I'm going to set that equal. Whenever you see an R and a T, so R is equal to 1.2 times 10 to the minus 2, because it's centimeters, divided by 2, because it said diameter. Our thickness is equal to 0.5 times 10 to the minus 3. So we need to see what is our R divided by T value, if that's greater than or equal to 10. Yep, we're allowed to use our thin-walled pressure vessel expression. So I'm going to say E1 equals EH, set it equal to 1 over Y times sig H minus mu times sig L. Let's define sig H equals del P times R divided by T. Sig L equals sig H divided by 2. Half of it, our hoop stress is always larger than that. That's our E1 equation. This is going to be our E2 equation. EHEL, sig L, sig H. Fantastic. We love thin-walled pressure vessel problems. 2 strain gauges of the material, strain measured along the 2 direction. So basically along the long direction. So that basically means that EL equals 0.0017. So right at the full stress strain sensors. So now actually I can solve. So I can say solve E2. Because now that I have EL, I just have to solve for del P. So del P gives me that. I can now go ahead and say with del P, set that equal to this. What's my sig H? What's my sig L? What's my EH? What's my E1? And then what's my E2? Well, yeah, once we, basically establish that. Full stress strain tensors, pressure, are we in a principal stress state? Yep. What's the maximum value of shear? That's always going to be basically sig H minus sig L divided by 2. That's going to be my maximum value of shear. Find the stress state for a 17-degree concentration for the maximum shear stress state. So, again, I can use my old partner here. Always handy to have these expressions in and ready to go. Stress ODG, I'm going to say sig OG. No, but I'm not going to do that because I don't want to. Actually, I do like sig OG. I'm going to say sig H, sig L, and then 0. So I need to find the stress state for 17 degrees counterrotation. So T dot sig OG. I'm already in, so let's say it like this. So I need theta goes to, if I rotate 14 degrees counterclockwise, or 45 degrees counterclockwise, that's positive, and that will put me in the maximum shear stress state plus another 17 degrees counterclockwise. And there it is. Don't you love linear algebra? And that is it. We'll see you in the next video. Thanks. Bye.